We can move next for our next talk by GV, and it's going to be, I think it's related in the sense that it has also stochastic gradient. So it's going to be about vqSGD. And GV, do you hear? Yes.
Okay. So, okay. Does it show my slides or?
Yes, yes. Yeah. Maybe if you make it full screen. Perfect.
Okay, let me just. Thanks again. Yeah, so first of all, like really thank you so much for organizing this. And also thank you everyone for joining. So I will be talking about this quantization schemes to which reduces communication cost and stochastic gradient descent. And this was a joint work with Raj, Daniel, Kane, and Arya. Okay. Yeah, so consider the following scenario. So assume you have a bunch of users communicating, bunch of users who want to collaboratively train some global machine learning model, okay, without really having to share their private data. And stochastic gradient descent is one widely used optimization subroutine used to train these large-scale models. And it proceeds essentially in multiple iterations. And in every iteration, you have 2 rounds. So in the first round, basically every local node computes and sends a local unbiased estimate of the local gradients to a parameter server. And the parameter server, on receiving these local gradients, averages them and updates the model and broadcasts them. Okay. And it is well known that the convergence of any such scheme directly depends on the variance of these unbiased estimates. And however, if you note, like communicating each of these gradients requires the local machines to send about d floating point numbers each. And in the setting of federated learning, where the number of nodes are really, really huge, or in the high dimensional setting, when these gradients lie in really high dimensional space, that is d is very large, this communication cost forms a bottleneck to the convergence or the efficiency of this entire stochastic gradient descent scheme. So the goal that we want to achieve today is to reduce this communication cost to a given budget of C bits per local machine. And with respect to this budget, we want to understand what is the best convergence that we can obtain. Okay. And this is, so just to rephrase the problem, the goal here is to compute an unbiased estimate of a gradient that lies in a really high dimensional real space that has only C bits of representation and also has a bounded second moment. Okay, so this is the problem setting. So we want to compute this unbiased estimate. And we work with the assumption that all of these gradients have some bounded norm. And without loss of generality, just by scaling, we can assume this norm to be 1, at most 1. Okay, so we want to quantize any gradient that lies in this unit ball. And our entire scheme is based on the observation that any unbiased estimate that has this finite representation is just a convex combination of a finite set of points. Okay, so you can take a bunch of points and write any point within the unit ball as a convex combination of these guys, and that will give you an unbiased estimate. However, there are many moving parts here. We want to understand how many points do we consider, how do you arrange these points in space, and also to understand the efficiency of computing the convex combinations. And understanding these questions will help you understand the trade-offs that you can achieve between communication and the variance of this stochastic gradient descent. Okay. So this is not a new problem. So one of the seminal works here, which was called qSGDs. So the way they quantize the gradients is by considering by covering this unit ball using many hypercubes or maybe hypergrids. Okay, so doing that, they achieve, they get an unbiased estimate of the gradient. And they have a variance that ranges from square root d all the way up to, that goes down all the way up to just a constant, with communication that increases from square root d all the way up to d indices in expectation. Okay, so as the communication increases, the variance decreases. That is what we know should happen. And then following this work, there were a series of works, all of which achieved various trade-offs. However, in all these works, the communication that was needed was at least square root d indices. Okay, so these are not bits, square root d indices. And the main question that we tackle is like, can we do better? Like, can we get communication below square root d as well?
GV, I may have missed something very quick. What is d here?
D is the dimension in which all these elements are like. Yes.
Yeah, thanks.
Yeah, so we propose a very generic vector quantization scheme. So consider the unit ball. And in order to quantize any point within the unit ball, we pick a set of points. Let's say the point set is denoted by C, and such that the convex hull of this point set contains the unit ball. Okay, so given this setup, any point within the unit ball can now be written as a convex linear combination of the vertices of this convex hull. And the quantization is essentially now, what it returns is just a vertex of this convex hull with probability proportional to the coefficient of this convex combination. Okay, so just by definition, this itself gives you an unbiased estimate. The variance here is now dominated by the circumradius of this convex hull, which is the maximum squared norm of any of the points within the point set. And now to communicate one of these vertices, all you have to do is return, send the index of this vertex with respect to some fixed ordering. Okay, so now the communication is just log of the size of this point set. So the number of points within the point set. Okay, so however, we don't know, like, so using different kinds of point sets, you can achieve different trade-offs, okay, between the communication and the variance. And so what I'll basically cover next is essentially how to construct these point sets and what are the trade-offs that we can achieve using various point sets. So first of all, we gave a characterization of point sets that contain this unit, such that the convex hull contains this unit ball. So essentially, the convex hull of any point set will contain the unit ball if and only if, for any point x on the unit sphere, there will exist at least one point from within the point set that will have a large inner product. Okay, so the inner product is at least one. So similarly, you take any point within on the unit sphere, there will always exist one point from within this point set C that will have inner product at least one. So this is a if and only if characterization, and using this characterization, we can construct point sets that achieve various trade-offs between communication and the variance. Okay, so we show that there always exists a point set of cardinality 2 to the little c, such that the variance is about d over c. Okay. And the proof is pretty simple. Essentially, what we do is we sample a large number of Gaussian points. By Gaussian points, I mean I sample 2 to the c points where every index of, where every point has sampled using IID Gaussian indices, okay, with certain variance. And the variance is chosen such that with high probability, the norm of each of these points is bounded by R, which is about D over C. Now to show that the convex hull of these, this point set, that is the point set with 2 to the C Gaussian points, will contain the unit ball, we show that the characterization is satisfied. Essentially, we show that if you pick any point on the unit sphere, there will exist one point from within this chosen point set that has large inner product. However, to do that, we need some kind of lower bound on the tail of this inequality. And now when we do a union bound, we essentially cannot basically do a union bound over all the points on the unit sphere. So we just take a union bound over the epsilon net points. Okay, so an epsilon net is just a discrete set of points on the unit sphere such that any point of the unit sphere is at a distance of at most epsilon from one of these net points. Okay, so there are exponential number of net points. So basically what we want from this tail bound is to grow exponentially. And essentially Gaussian points allows us to achieve that. And using this set of points, we get an unbiased estimate, and the variance is about D over C. And the communication that we need is log of cardinality, which is that of that is exactly little c.
How hard is it to find these this epsilon net, the complexity of it?
Yeah, so again, so this is kind of inefficient way of getting it. Epsilon nets
random work.
Yeah, so if you take any covering code, that will give you an epsilon net. Like you project it on the unit sphere.
So one quick point, Salim, here, actually, this is just, if we need the epsilon net for the proof, we really need to construct it, right? So it doesn't really matter. We just want to show something.
Okay, okay.
Yeah. Okay. So what this random sampling tells you is that we can achieve the following trade-offs. That is, communication times variance is about oddity. So for any C bits of communication, you can achieve a variance which goes as D over C. However, this is a randomized construction, and one goal of this work is to understand, can we get explicit constructions of such point sets? Okay. So on one end of the spectrum, you see that if you take any epsilon net, and if you just scale this epsilon net by a tiny constant, that will satisfy the constraint that the convex hull will contain the unit ball. Okay, and this already gives you an unbiased estimate that has a constant variance, and communication now is about D bits. Okay, so here the communication is large, but the variance is the best we can hope. However, computing this convex combinations here with respect to these epsilon nets is slightly computationally inefficient. So we look at another explicit construction. So this is based on Reed-Muller codes. So for this construction, let us assume the dimension is some power of 2. And now consider just the set of all code words of Reed-Muller codes of degree 1 in L variables. Okay, so a Reed-Muller code is of degree 1 is essentially evaluations of all linear polynomials over all the field elements of F2 to the L. Okay, so the code book will look something like this matrix here. So the number of code words is about 2D, that is 2 to the L plus 1. And each of these are evaluated over all the points in F2 to the L. Okay. Now, just by mapping these points from the binaries to the reals using a simple BPSK mapping, just map zeros to -1s. So each row here of this matrix corresponds to a point of the point set that we will be taking. So each point has a squared norm of at most, has squared norm D exactly. And this will give us an unbiased estimate, which has a variance of order D. And since the number of points in this point set is exactly 2 times D, so the communication that we achieve is about log 2D. Okay. So this was a very simple construction. And also computing these convex combinations is efficient because it is essentially a Hadamard matrix that you are doing a linear, that you're solving a linear system of equations on. Okay, so this is an efficient way to construct. And now here you see the trade-offs is, so for about log D bits of communication, you achieve a variance of D. And what we see is that if you use any binary linear code instead of the Reed-Muller codes, that will also achieve the same variance bounds. And with Reed-Mullers, this is the best communication we can hope for. And one way of improving variance is just by using a repetition. So now you can start with a scheme that has high variance, but low communication, but you can do a smooth trade-offs with, by increasing the communication a bit, you can keep reducing the variance. And the idea is a simple repetition scheme. So you can just apply the quantization scheme independently some S times and take an average of it. So that will reduce the variance by a factor of S. But now communicating this average is a little tricky because the average does not lie within the point set. So you cannot simply send one particular index. But we can get away with it by sending S different indices that you obtain by applying this quantization schemes S times independently. So that will increase the communication by a factor of S and the variance reduced by the same factor. Okay, so the product variance times communication still remains the same. So if you start with the previous scheme, that is of the Reed-Muller codes, so initially, so for S being 1, you know that the communication is log D and the variance is about D. But as you keep repeating it multiple times, you can increase your communication and get a smooth trade-offs between communication and variance. Okay. And this scheme, essentially what we see is just a generalization of the previous, or most of the previous quantization schemes. So the QSGD is just a specific case of this entire quantization scheme that I've just described. So if you take the set of points to be the set of all some S sparse vectors, then the point set to be the set of all S sparse binary vectors, then what you end up is just the the QSGD scheme. Okay. So our scheme generalizes most of the previous quantization schemes. And as a bonus, what we get is that this vector quantization scheme also preserves privacy. Okay, so which is very important parameter here to understand, because even in federated learning models, you don't really want to share your private data. So preserving privacy is of utmost importance. And we see that vqSGD scheme directly preserves privacy as well, like certain instances do. And by privacy, I refer to the notion of differential privacy. That is, by looking at the output, you basically want your inputs to be indistinguishable. So any close-by inputs to be indistinguishable. And in fact, what we show here is a stronger notion. We show that any two gradients will be indistinguishable. So previously, in terms of private gradient quantization, the previous work, the best known work was that of CPSGD, where the authors added some binomial or discrete noise to quantized gradients to achieve privacy. And here now the communication now varies as, which is a parameter of the amount of noise that you want to add. And that depends on the privacy parameters that you want. However, the communication is still large. So you need at least D bits of communication here to get an unbiased estimate of the gradient, and the variance is about D. And what we show in that using certain point sets, the vector quantization directly gives you privacy. So you don't really need to add further noise to the quantized gradients. And the idea is very simple. That is, if you take any 2 points within the unit ball, yes, and if you look at the mapping to a particular vertex of the point set, then the privacy here is preserved, because most points will have, so close by points will have very little variance in terms of the coefficients of the convex combinations. Okay. So what we get is privacy. However, it is not for free. We pay for privacy in terms of variance bounds. However, the communication remains the same. So we do not incur additional communication cost to achieve privacy here. So one very simple construction that we consider here is that of a cross-polytope scheme. So consider this set of 2D points where each point is essentially a scaled standard unit vector. Okay, so you take all the unit vectors, so plus minus EI, scale it by root D. So we can see that this point set satisfies the characterization. That is, the unit ball will be contained within the convex hull of this point set. Okay, so this directly gives you an unbiased estimate with a variance of about D, and the communication is log D. However, the scheme, as we can show very easily, also achieves privacy. However, the privacy parameter is not the best that we can do. We can improve on these things. And in fact, what we show is that any vqSGD scheme can be made differentially private for any privacy parameter epsilon. And what we get is epsilon 0 privacy instead of epsilon delta privacy that was achieved by the previous works. And the way we do it is using a randomized response scheme over our quantization scheme. So randomized response scheme was initially suggested by Warner in 65. So the idea is like whenever you get an output of the quantization, you basically send the correct answer with certain probability, or you send a different vertex with a different probability. And just by this randomizing this response will get you a privacy of epsilon for any epsilon larger than 0. However, the price of privacy here is paid by an increased variance term. So so the variance term increased by a factor of size of the cardinality of the point set. However, the communication still remains small. And moreover, we also show experimentally that using our vector quantization scheme, in particular with the cross-polytope with certain number of repetitions, we are able to beat the performance relative to the qSGD scheme. And we do that even with way fewer communication compared to qSGD. So in summary, what we suggest is a vector quantization scheme. So the scheme is based on the convex hull of point set, and based on various points that you choose, you get different trade-offs between variance and communication. The best that we can get is using a random sampling. The explicit constructions that we suggest are a factor of log away from reaching the optimal. However, for a constant variance term, we reach the optimal using epsilon nets. Moreover, we also see that some of these quantization schemes also give us privacy directly. And also, like any other non-private quantization scheme can be made private using a randomized response scheme. And this entire thing generalizes all the previous quantization schemes that were suggested in literature, most of them. And finally, I want to end with a set of open questions. So essentially, we still don't know whether what we achieve, that is variance times communication being equal to D, if that is optimal for any unbiased estimate. However, for a constant variance, we know this is optimal. But for something which is, for anything which is like sublinear communication, we don't know whether our schemes are optimal or not. Moreover, the explicit constructions that we have are a factor of log D away from the randomized ones. So one way to achieve this is probably using a union of polytopes, or maybe some other Minkowski sum of polytopes or something like that, that can probably improve on the bounds. And finally, like we still want to investigate what are the optimal trade-offs between private quantization. So if you want to achieve any privacy, then what are the trade-offs that you have to do in terms of, so what is the price for privacy that we pay in terms of communication and variance? And yeah, so that's it. Thank you.
Thanks a lot, GV. By the way, there is an option down there to clap. So I just clapped, so you can use it. And then there's a chat that I saw that there's some activity on the chat, which is very nice. So if you have a question and so on and so forth. I think we have time for a very, very quick question to GV. If anyone has a question before we move to the next talk. If there's no question, I can ask a question.
Sure.
One very quick question. So I'm very interested in the statement you said that Reed-Muller codes here are optimal in terms of, you said communication cost. And in what sense? And I mean, I was I'm very curious why Reed-Muller codes.
So they are basically, we are getting to Hadamard matrices in some sense. So Reed-Muller codes are optimal because the number of code words, so we are looking at linear Reed-Muller codes. So degree 1 Reed-Muller codes.
But yeah.
So degree 1 Reed-Muller codes, the number of code words are the least that you can get. So it's about 2D. Okay, so for any D-dimensional code, you have only 2D code words here. And we see that for any other binary linear code, we achieve the same variance bound. So in terms of variance, we cannot improve. So the only way we can improve is by reducing communication. And you cannot do anything less than log D anyway.
Okay. Thanks a lot, GV, again.